I'm glad to be here with my esteemed colleague. I'm going to talk about persistent memory support in the Windows environment, and Stephen's going to talk about it in the Linux environment. We get about 10 minutes to blast through this. I just want to make you aware that persistent memory support has been in Windows since the 2015 timeframe. There's examples where it's available, and both in Server 2016 and the recently released Server 2019 has full persistent memory support as well as various client workstations. I just briefly want to do a little bit of overhead or review of what DAX is. Again, its advantages, and it's already been talked about, is improving I/O performance. It does, from a file system perspective and an OS perspective, there are disadvantages to it, and that is that there's certain functionality you lose. For example, software level encryption and compression is just an example. And the reason why is when you're doing this direct access model, you lose the OS hook points. You don't have the ability to do these transformations in software anymore. And on the Windows environment, we support DAX through the NTFS file system. This is a picture. We've seen various versions of this same picture. I won't dive into it in detail. But basically, we have a persistent memory-aware file system. There's applications that understand it. There's applications that don't. And applications can do direct access to the persistent memory. In the Windows environment, I just want to point out, because there's been confusion on this in the past, we do support normal cached, non-cached read-write APIs on a DAX volume. In the Windows environment, we convert non-cached into cached I/O, and then we do not go down through the storage stack anymore. The file system does all the copies between any cached I/O, non-cached I/O directly into the persistent memory. So even on a DAX environment, even if you're using traditional APIs for compatibility, as Andy was talking about, you eliminate a lot of overhead as the file system will copy that data directly into the persistence. And then, as we said, memory mapped I/O is direct to the hardware. What we call it is zero copy access to the persistent memory hardware. We also have block mode volumes. Again, it's for full compatibility. We do support sector level atomicity. This was one of the questions that came out is, hey, what if you lose power in the middle of these things? There is this feature called BTT, the block translation table, that we use in our persistent memory driver that gives us sector level atomicity in block mode environments. And so you don't have to worry about any of that stuff. And again, block mode is fully compatible with the whole system. You can do software encryption, compression, everything. Works on all the Windows file systems. One of the things that was introduced in Server 2019 is that we now have full, well, it was actually introduced earlier on Workstation, but on the server side is we have full HyperV support, so we have full virtualization. And we support both Windows and Linux guests on top of this HyperV environment. And just to be clear about this, in a virtualized environment, if you have your VHD sitting on persistent memory on a DAX volume, you are getting direct access out of the guest OS to that hardware. So you're eliminating, again, a ton of overhead of going through the guest file system, the host file system. And in our world, we actually have a new VHD file type called a VHD PMEM. I'm not going to talk about this thing. I just put it in there. You can look at it later if you so desire, if you don't know what large and huge page is in. One of the things we added in Server 2019 is support for large and huge pages with persistent memory. This is all about performance. One of the side effects of this is we had to ramp up our file system, the NTFS file system, to support 2 meg cluster sizes. This is just saying that we introduced a lot of management applets through PowerShell in Windows in Server 2019. Also, as Andy alluded to, we do have support for the PMDK. It's been available since Server 2016. This is this programming model that helps make apps use it better. And it's available on GitHub, and there's a link. I want to talk in my time remaining, which I blasted through that pretty fast. I'm doing good. I want to talk about 2 examples of usage of persistent memory, and this kind of goes back to what Paul was talking about. One is in SQL Server 2016, and this is at the time frame when we had these small NVDIMMs. We're talking about 16 gigabytes, maybe 32 gigabyte NVDIMM-N devices. They did this small change called tail of the log. And basically, they used the persistent memory in DAX mode to put the tail of the log to it. And they saw a 2x gain in performance of running of the database performance. And this was accomplished because they have their transaction latency by putting it on this much more performant location. And then they also deserialized their SQL logging threads. And so again, actually a very minor change to SQL gave them 2x performance by leveraging DAX persistent memory. And then this last one I want to talk about before turning over to Stephen is we talked about this at Ignite 18. And it's basically a real-world application. As been pointed out, you really need to replicate your data. It doesn't make sense for data that you need to persist to keep it on a local machine, and if that machine dies, your data's lost. So one of the important things in this whole persistent memory world is you need to make copies of your data and do redundancy. This is an example of a 12-node cluster with triple redundancy, triple mirrored data. It is using, if I can point, oh, there we go. So what we have is we have 3 persistent memory volumes, and if you look, this is, I'll use the official name, Intel Optane DC persistent memory. It's using it as a cache. And this is going over a 25 gigabit network. And so the hardware specs are there. But what we really did is the performance gain. With this setup, with this caching layer right here, we were able to get 13.8 million IOPS in this environment that was demonstrated at Ignite. And if you look at the actual throughput of 549 gigabytes per second throughput, it's an impressive number for a 12-node cluster with triple replicated. And in fact, you can see some of the latency times of 250 microseconds there for end-to-end writes. And the remote writes were taking about 180 microseconds. And again, this was using RDMA. It was Paul that was talking about networking and everything. RDMA is the way to go. What's interesting about this is that the persistent memory was actually running in block mode. This was not even in DAX mode. And so there's lots of improvements that can be done to this to make it much more performant. And we'll do those things over time. That is everything I have. I'll turn the time over to Stephen. Go ahead.
Hear me?
Or wherever you want to be.
I think the Linux logo is so much better than the Windows logo. Woo! Hands up if you were at the hackathon yesterday, the persistent memory. So you got a free pass. You can go get a beer. Come back in about 10 minutes. So Neal talked about Linux support in Windows. Persistent memory support in Windows. I'm going to do the same for Linux. The takeaway is Linux, as it is right now, has fantastic support for persistent memory. And then using the same PMDK libraries that Andy talked about that also work on Windows, you can get library access on top of the operating system to support to build really interesting applications or convert existing applications over. So that's really important. I have a lot of detail on this, so I think I'm going to run through this super quick. People take pictures or look at the slides later. There's lots of links to interesting things there. But for me, one of the things is when I get on a new system for the first time via SSH, I don't even know if there's persistent memory in the system. Like I got 100 machines in my lab. Some of them do, some of them don't. Like, how do I know? So one of the first things I wanted to show people was how do you actually get onto a system? Like once you're in a system, how do you even know what the NVDIMMs are? How big are they? How are they configured? What vendors are they? Are they the ones you expect, et cetera, et cetera. So we have a tool for that. It's called ND Control or NVDIMM Control. Open source tool, runs in user space. You can either install it via your favorite package manager if you run RHEL or CentOS or Debian. Or you can download the source from GitHub and compile it yourself. And during yesterday's hackathon, one of the first things we did was we actually started to do some ND control list commands just to see, do we actually have NVDIMMs? Now, if you don't see any NVDIMMs listed, there's one of two things going on. You SSH'd into the wrong machine, if you don't actually have NVDIMMs in there, or the operating system doesn't actually have the enablement or hasn't been turned on to support NVDIMM. So one of the other things, I'm not going to cover today, but we did in the hackathon, And this is my plug for all of you to sign up for the next hackathon, right, which is going to be at the Non-Volatile Memory Workshop in San Diego in a couple of months, is we showed people how to make sure that the Linux kernel you're running has been configured in a way that enables access to persistent memory. Right? Now, if you just typically use the kernel that's provided by your distro, it's probably on already. It certainly is in things like RHEL, Fedora, Debian, and Ubuntu. But if you're like me and you're like building your own kernels, you have to make sure you turn certain things on in order to get access. And that's the same kind of access that Neal talked about. So things like DAX, persistent memory block mode, and so forth. Persistent memory in Linux, like in Windows, can be just treated like a block device. I love the data in your last slide, Neal. He showed some amazing performance benefits just by treating a persistent memory device as a block device. Applications didn't have to change. And you still saw a significant performance boost just because of the underlying characteristics of that persistent memory. We can do the same in Linux, and the great thing is you can use all your favorite tools, FIO, DD, IOZone, and you can do performance analysis against that persistent memory device like you would against an SSD or a hard drive. You can RAID this stuff. You can do device mappers. You can do MD. You can put RAID over the top. You can put software RAID over the top. There might be repercussions in doing that because now you have software in the path of this super fast device. But you can use all your favorite block layer tools to do that. So go have fun with that. One of the things we typically do with a block device is put a file system on top. In Linux, we have the same concept of DAX, direct access. Not every file system that's in Linux today supports DAX. In fact, only a few do. So if you put a file system today on a persistent memory device that doesn't support DAX, you will not get all the performance benefits of that underlying media. Right now, as of today, it's XFS, ext2, and ext4, which happen to be some of the most popular file systems. But there's a whole bunch of other ones out there that either aren't going to get converted or need to get converted. One of the great things about Linux that I don't work for Microsoft, so I don't get to see the Windows source code. In fact, even if I did, I don't know if they'd give me access because they know what I'm like on LinkedIn. I just post the whole thing. But the great thing is for Linux, I can just go to a website and I can see the entire source code. And not even just today's Linux source code. I can go back in time and look at every single Git commit that's gone into Linux. So the great thing is if you don't like something in Linux, change the source code and recompile it, and you've got what you wanted. Right? Now, that's not always trivial, but it's certainly something you can do. So one of the great things about Linux is you can actually get in, look at the source code, and see what actually works under the hood. And so we can do that with the file systems as well. And then kind of segueing into the world of PMDK, which is an awesome, awesome library set. And thank you very much, Andy and his team, for really being the kind of drivers of that. But once you have a file system on a DAX-aware persistent memory device, you can write an application that uses the mmap system call, map that into a virtual address space inside your program, and you basically have direct access to persistent memory. Like Andy said, at that point, you can bit bang on that persistent memory, or you can use some of the library features provided by things like PMDK to do much more concrete things that are the helper functions in those libraries provide you. And they've done it in a way that makes sure that things are consistent, that are fault tolerant, that are safe. And you as an application integrator can tie into your applications or even write brand new applications using things like the key value primitives. Okay? So that, again, is really a fun area to explore. One of the things I didn't actually cover, I think Neal touched on it, is very, very important. If you want to get started with persistent memory, I recommend doing something similar to what we did at the hackathon, and SNE is going to have some tutorials on how you can do this yourself at home. Google Cloud are now alphaing Optane DIMM-enabled servers in the cloud, so it's not completely public domain access yet. You have to kind of go through an approval process, but I think the plan is eventually you'll be able to go and buy or rent a server in Google Cloud that has Optane in it. And obviously, other public cloud vendors may or may not decide to do something similar. Neal. Once you have an Optane enable thing, you can do some pretty interesting things with hypervisors. So Neal talked about HyperV support. KVM, which is the Linux equivalent of HyperV, this virtualizer that's built into the kernel, also has very, very good support for real persistent memory and passing subsets of that persistent memory through to virtual machines. So now you can do fun stuff like rent a Google Cloud instance for a few days. You can put KVM on that. You can create a virtualized environment. You can put a few VMs, and you can carve up a reasonably large amount of Optane DIMM, for example, and give pieces of that to different VMs that are themselves running a different operating system, which may or may not be Linux. So you could actually have a Windows VM sitting on top of KVM looking at persistent memory, or you can have a Linux VM sitting on top of Linux, or we can have a Linux VM sitting on top of HyperV. And I think for people who want to get their hands dirty with persistent memory, who maybe don't have the budget or the ability or the scale to go and get Intel to ship them some of these machines, get on the public cloud. That's going to be happening very soon. And SNIA is going to have all the hackathon material up on GitHub. So even if you can't make it to a physical hackathon, the idea will be that you'll be able to follow along from home. And I hope that people take a note of that and maybe go do that as soon as they can get access to something.
Yep.
Okay.
Thank you.
That's kind of all I had. Thank you.
I did want to make a comment on Paul's slides. One was he was talking about different uses of persistent memory in that one slide. One that he didn't include, but I think you should think about for the future is I think once we get persistent memory on client, I think the gaming industry is going to go crazy with how to leverage and use this. And so it's one of those areas to think about. I'm sure those guys at some point will really start innovating in how to use persistent memory to make really awesome and faster games.
Very good. All right, we have a few minutes, which is cool. So time for some Q&A for the esteemed speakers.
Hi, I'm Bill Gervasi from Nantero. And I have a question about there's two different classes of persistent memory. There's a memory class storage, like an NVDIMM-N, that has a fixed capacity, and it's always going to be that capacity. Then there's a storage class memory aspect of persistent memory, where there's...
You're in a room full of SNIA people.
I'm not a SNIA guy. That has bit rot. And so I'm curious, how do you guys handle the bit rot, where your 3 terabyte drive becomes 2.5 terabytes over time?
Well,
is the memory allocator gracefully handling that rot, or do you guys expect over-provisioning and some communication?
I'll talk about Linux, right? So in Linux, we tie into other standards like JEDEC, ACPI, UFI, who are all defining low-level interfaces by which the system management things in the server can communicate with the NVDIMMs. So there is metadata in there. There's things like labels. There's ACPI register spaces. And they give us information about what type of memory is this? We have what's called heterogeneous memory attribute tables coming. They're going to tell us, is this memory just DRAM with some kind of FPGA-based NAND backup, or is this something that has some endurance requirements and so forth? When you go into raw DAX mode, like when you're accessing that material, if the device is chosen to expose all its capacity to you at that point in time, then it's up to you as direct access program developers to manage the fact that that might get smaller on you. And in fact, it probably won't even be allowed to be. That will just start causing serious problems. We do have something called poison, so we can already say, wow. We can already say things like, some of the physical media has gone bad. We know where it is, and we, as the operating system, can mark that as bad with poison, and we can basically notify applications, you don't want to access this particular region, right? And so that's one way of handling. Another way of handling is in a vendor-specific way, where you have more capacity than you advertise to the outside world. And you can choose to manage that in some proprietary way behind some kind of controller. And that may be something that Intel does today or not. I mean, I don't know. I don't work for them, so I don't know which of those methods they choose. And but that would be totally vendor-specific and wouldn't be part of the operating system.
Same thing on the Windows platform is you can do basically bad block hot fixing when you're dealing with it through the file system. We support the poison features, this stuff, and it's getting better. I mean, these initial NVDIMM-Ns didn't have a lot of stuff. As the standards improve, there's getting more and better handling of this going forward. It is a very legitimate concern, and good handling of it is important.
Neal's point, people are starting to get a sense of what vendor-agnostic things need to be exposed by these devices, and how does the operating system then consume those vendor-agnostic mechanisms and do something useful with it.
Yes.
And we're not final on that. We're still iterating as people realize, I need some way of seeing how many more cycles I got.
Right.
Or I need some way of knowing where my bad blocks are. And we'll continue, SNIA will continue to drive that through different organizations.
Yeah, it's very useful. I know one of the things we do in the Windows environment is we can get from the BIOS the bad pages. And if you have a file with some bad blocks in it, we just don't allow you to map it. It's a very simple answer that we give right today is you just can't map that file. Then it becomes your job to find a copy and put it in different locations so you don't have that problem anymore.
All right, another question in the back.
So, am I not talking too loud? Oh, so you mentioned that you both integrated the PMDK into your software stack.
Yes.
Is the PMDK the de facto standard? Is that a SNIA spec that people can follow and create, or is that?
What's the answer, Andy?
Officially, what is it? I think one thing to make clear is we haven't integrated that into Linux or Windows. It's like, that's a user space library that's written in a manner that it can be compiled on a Windows system or compiled and used on a Linux system.
And those APIs are identical. In theory, you should be able to take an app and move it between the two and just recompile.
Yeah.
So
And it is on GitHub. In the presentation that we have, the GitHub link is there.
So, is there any plans to standardize it?
Well, it came from a standard. We had the programming model that was done within SNIA, and that was used as kind of the golden reference by which, mainly Andy as the architect went forward and wrote that library.
And just to be clear, it wasn't done just by Intel. There were multiple companies involved in its implementation.
And it's not done. It's an open source project. So if you don't like something, feel free to send a pull request.
Yes.
Thank you.
Time for one more.
Everyone wants their coffee.
Everyone wants their coffee. All right, there you go. All right, we'll have 10:29. We're 1 minute to the good. Good job, folks. So we'll resume at 10:45 on the button. 10:45. Thank you.